it's this thing. Okay, so for today, we're looking at, we really did graphing linear inequalities. I am going to show you how to do that using technology today. I'm going to show you how to do it using Desmos. I don't think I'll even mess around really with TI-84s. We'll just do this on Desmos because that's what you'll be using. We want to look at how we solve systems of linear inequalities, and really we're just solving by graphing. That's the only way we're going to solve these things. And then we'll look at just a couple applications and call it a day. So why don't everybody go ahead and click and close, have a quick look up here, and I'll be as brief as I can and cover the material so I can get you going. I know your time is precious and I want to get you working, but we do have to look at a couple things. So what about something like this? We've got a compound inequality here. What do you think we would do with a situation like this where y has to be greater than or equal to 1 and less than 3? What do you think is happening there? What do you think? Okay, yeah, there's really two inequalities in one here, aren't there? Right? This actually is a system because there are two inequalities. We wrote it as a compound inequality, but there are two parts to this. Here's one of them right there, right? We could write the inequality y is greater than or equal to 1, and here's another one. Y is less than 3, right? Those are both pretty easy ones to graph. If we graph the top one, the boundary line is really simple. Y equals 1. What's that look like? Yep, straight horizontal line at 1. Is it going to be dashed or solid? It can be solid. Okay, so we get something like that. And we're going to shade above or below? Above, yeah. Okay, so something like this. Oops, not that, like that. Yeah, I guess that'll work. Something like that, right? The other one, we get a dashed or solid boundary line. Dashed. And that's going to be at 3, right? Whoops, I don't want that. And I'm shading below. So then, what's the solution? Think what the solution of a system meant with lines. It meant the places where the lines intersected, right? So it was the point where that was on both lines at the same time. It was graphed twice. So it's going to be the double shaded region, isn't it? It's going to be just this region in here. It's going to have a solid boundary line on the bottom, a dashed boundary line on the top, and it's this one little strip of, it's infinite strip, but it's that little strip of values between the two lines. That's my solution, okay? Give me 1 to 5 on that. Does that make sense? Okay. Okay, that's pretty good. So then here's how we deal with this. If we're graphing a system of linear equalities, it's super simple. We're just going to graph and shade each inequality individually, and then we're looking for the region that overlaps. And if we graph 2 inequalities, it's got to be the region that overlaps with both of these. What if I graphed 4 inequalities? What would be the solution? Okay, it'd have to be, if I had 4 inequalities, it'd have to be the one that overlapped 4 times, where all 4 of them were shaded. So it might be a pretty small region, or there might be none, right? Okay, so let's try this. Let's maybe, I think I'm just going to do this one using technology, and we'll do the next one. We'll graph the next one because this one's pretty simple. So if I were to do this on Desmos, here's what I'd get. Here's how this works in Desmos. It's exactly as easy as it looks. I'm just going to put these things in exactly the way they're written, okay? So the first one, here's the blue one. Oops, that's not blue. Here's the blue one. right? Just put it in just like that, and look what it does. It graphs this blue region. It gives me a solid line, and if I had put in just an inequality, it would have looked dashed. Let me just show you this to you, because I think maybe you better see the steps. Very simple, but probably better if I do. So all I'm doing, I'm just going to go into Desmos and type this in. Now, how, you might ask, how do you get a less than or equal to? Anybody know? I just go less than, and I could pull this thing up on the bottom, it's true. I don't have to though. I can just go less than and then type in equals, and it puts them together, okay? So y is less than or equal to negative 2/3, oops, what'd I do here? 2, yeah, I think I had something screwed up here. Negative 2/3 x minus 1. Now I'm going to make this blue so it matches the other one. Okay, there it is. Right, no big deal. Now what happens if I change this to just a less than? Look what it did. Okay, it gave me a dashed line. So it does everything for you, right? But we want it to be solid. All right, next one. Okay, next one, y is greater than or equal to. So I hit greater than, equal sign, 1/2 x minus 8. We want this one to be red, so I'll make it red. And there it is. Okay, and if I need to know, like if I wanted to know some specifics, like where are the intercepts and where does it intersect, I can still do that stuff, right? I can still find all these points if I want to. Okay? Same way I did before. All right, so there's one example. Let's try one of these just to remind ourselves how we graph these things. Let's try one of these. How about this one? What am I going to have to do here? Okay, good. Got to put it in slope-intercept. Y equals mx plus b form. So let's do this one first. To get that one in slope-intercept form, what do I have to do? Okay, good. Subtract the 7x to the other side. We're going to move this guy over, and that's going to give us 3y is less than or equal to, I'm going to get a negative 7x on that side, right? Plus 18, and then I'm going to divide by 3. Good. So we end up with y is less than or equal to negative 7/3 x plus 6. Everybody agree? Okay? So let's graph this. How am I going to graph that line? Okay, start at 6, because that's B, right? Everybody give me thumbs on that. Does that make sense? Phone should be away, please. Okay, good. We're starting on 6. So 1, 2, 3, 4, 5, 6, right there. And how about my slope triangle? There you go. Good. Down, rise -7, run 3. Okay, so we get -7, +3. There's my other point. Solid or dashed boundary? Solid. Okay. Shading above or below? Give me thumbs up for above, thumbs down for below. Okay, good. And we can tell, can't we, by, that part right there, that's telling us we're shading down. And so we get this. Okay, next one. What am I going to do there? Okay. And if I do that, I'm going to get negative 3y is less than or equal to, I've got a negative 2x on this side now, plus 9. Okay, now what? Okay, what do I have to remember to do? Good, I've got to remember to switch the inequalities, don't I? Because I'm dividing by a negative. So that's going to get flipped around. And I get the negative 3's cancel. I get a y. Negative 2 divided by negative 3 is positive 2/3 x. 9 divided by negative 3 is negative 3, right? Okay, how am I going to graph this one? Okay, start at negative 3. My slope triangle takes me up 2 over 3. So there's my point of intersection. Solid or dashed? Solid. Shading above or below? Above. Good. Okay, and we can see that right there, can't we? We want the line that's greater than, we want the y values greater than the boundary line. So then we end up with, that, right? It's kind of hard to see what's going on there, but here's the region. The overlapping region is going to be just this piece up here, isn't it? See if I can make that a little better. And the boundaries of the region are both solid. So that's everything in purple is our solution then. Okay, give me 1 to 5. Okay, it's really pretty easy stuff, isn't it? And then I thought I included, did I not? Well, I guess I didn't include a Desmos on that one. Okay, let's look at one more of these. How about this? And I think this is probably good. Get through this one, I think we're good. So we had a little application here. Darcy's buying apples and oranges for a large fruit basket to give away as a door prize at a charity event. Apples cost 24 cents each, and oranges cost 80 cents each. She has $12 to spend and would like to purchase at least 20 pieces of fruit in total. Okay, so if we're going to set this thing up, what's always our first step here? Find the variables. Good, so we need to know what the variables are. What are they? What are the two things that we can vary? Okay, good, the amount, the number of apples and the number of oranges. The prices are already set, aren't they? Right, we can't affect that. That's the stores setting those. But we can affect how many we buy. So X, we'll just make that number of apples. Y is the number of oranges. We got to come up with a couple equations then. So how about, let's start with an easy one. How about this one right here? She'd like to purchase at least 20 pieces of fruit total. How are we going to say that one? Clayson, you have an idea about that one? Say it again? Oh, close. But now she wants a total of 20 pieces of fruit, so that's including, it sounds like, both apples and oranges. Ah, okay, so x plus y would be greater than or equal to 20. That makes sense? Okay. So there's one equation. X plus y is greater than or equal to 20. Okay. We need one more. It's not an equation, an inequality, right? We need one more. What do we got here? So she has $12 to spend. Now that's a little trickier. She has $12 to spend. Apples cost 24 cents. Oranges cost 80 cents. She has $12 to spend. So what's that telling us? If she has $12 to spend, what's that telling us about the cost of the fruit she's buying? Oh, max is 12, so as an inequality, what would the cost have to be? Less than or equal to 12. Okay, so we just need an expression that's going to predict the cost, right? We know that apples cost 24 cents each, and we're buying X of them. So, okay, good. So we're going to write this in dollars. So 0.24x, that's going to be the cost of all the apples, agreed, in dollars, plus 0.80y, right, has to be less than or equal to the amount of money she's got, which is 12. Okay, make sense? Okay, now let's try this. Let's just graph this in Desmos and just see what happens here real quick. We're looking for the shaded regions. There's one other just little, I mean, this is, I don't even know if they meant to do it this way, but I want to show you one other part of this that, that's going to be interesting. Okay, so let's try this first one. X plus y is greater than or equal to 20. Okay, so there it is. Let's make it red. So it matches our graph. And then the bottom one. We'll just use Desmos. We could solve this manually if we wanted to, but we don't need to. 0.24x plus 0.80y is less than or equal to 12. So let's make that blue. Okay, so that represents, there's the solution set. If I zoom out, does anybody see anything wrong with that maybe? So all these points, all the ordered pairs in that shaded region should represent solutions, right? So for example, if I pick a point, can I not do that? Oh, maybe not. Here, I'm going to be tricky. So let me do, so I'm going to pick a point. I can just move these points around a little bit. Let me make this point a different color so it sticks out. I'm going to make it green. Okay, look at the coordinates of that point. So that one works, right? That's 30, 5. It's in the shaded region. So what's that telling me about a possible combination of fruit that she could buy? 30 apples, 5 oranges. Everybody agree? Okay. I could go down and I could also buy 38 apples and 3 oranges if I wanted to. Okay. But according to this graph, I could do something a little strange. Does that make sense? Because that's in the shaded region. Okay, what's wrong with that? It says I could buy 38 apples and -9 oranges. Yeah, you can't buy -9 oranges, right? That's not possible to do. So what's wrong with this? What other inequality should we maybe include here? If X is the number of apples and Y is the number of oranges, in order for this to make sense, not just mathematically, because mathematically that graph made total sense, but we got to be careful when we're modeling stuff with math, because sometimes if we're not careful, the math can model some things that are non-physical, that don't make sense in the physical world, right? How about that? Y is greater than or equal to 0. Doesn't that make sense? Because if y is the number of oranges, you can't buy a negative number of oranges. You have to buy 0 or more oranges. Agreed? So it seems a little silly that we have to put that in there, but it really is something that we probably need to include if we're going to make this, if it's going to make sense in the physical world. All right, so we're going to add y is greater than or equal to 0. And while we're at it, we probably should also do x is greater than or equal to 0, right? Although in our case, that didn't really impact the graph at all, right? And now if we plug that in, look what happens. Yeah, now that looks a little better, doesn't it? Now we get this one region in here. How's that? I guess that's better. So we get this one region in here that makes sense. Right now I can only pick values, positive values of x and y, or 0, right? I could choose, if I wanted to, for example, I could choose to buy, where is it? There it is. I could choose to buy no oranges and 38 apples, or I could even buy more. I could buy 49 apples and 0 oranges, and that's in the bounded region, isn't it? Because it's a solid boundary line. Okay, everybody give me 1 to 5 on that. Okay? All right, so here's, it's kind of messy looking, but there's a copy of that, what we just did. It just wants you to give 2 possible combinations of apples and oranges that Darcy could buy. Well, we already gave a few, right? Anything that's in that, the region that's shaded by all the inequalities, any of those ordered pairs would do, okay? All right, I think I'm going to turn you loose on this. I feel like that's probably enough. I had one more example, but I just don't know if we need it. I think that's good.